Hello, everybody. Welcome to Ms. McGuire online video lectures. We covering bones and osseous tissue, and today we will talk about physiology of bones. So let's go ahead and begin. Osteogenesis or ossification is a bone tissue formation. It has several stages. Bone formation that begins in the second month of development, so that's prenatal development before baby is born. We also have postnatal bone growth until early adulthood, and bone remodeling and repair happens through the lifetime, so it's a lifelong process. When we talk about ossification or formation of bones, we have two types of ossification, intramembranous and endochondral. The word intramembranous means ossification happens inside a membrane, and endochondral tells you that ossification happens inside the cartilage, because chondral means cartilage. So intramembranous ossification, bone develops from fibrous membrane. Bones that are formed by this type of ossification are bones of the skull, including frontal, occipital, temporal, part of the mandible, maxilla, and part of the clavicle. Endochondral ossification, bone formed by replacing hyaline cartilage, and most of the skeleton is formed by endochondral ossification. Actually, all the skeleton below the skull, with the exception of clavicle, formed by endochondral ossification. Okay, so let's look at the steps in intramembranous ossification. So we're going to start with embryonic tissue that form a membrane. Now, those cells are embryonic cells called mesenchymal cells. Then ossification center appears in a fibrous connective tissue membrane. Selected centrally located mesenchymal cells cluster and differentiate into fibroblasts, forming ossification center. Now, those cells that are embryonic stem cells, mesenchymal cells, they will differentiate to osteoblast. And osteoblast, we know the osteoblasts are the cells that secrete osteoid and form bone, right? So this differentiation is called ossification center, right? So we form ossification center when mesenchymal cells clustered and differentiated into osteoblast. Then bone matrix osteoid is secreted within the fibrous membrane and calcifies. Now, if you have our osteoblast, they start secreting osteoid. Osteoid calcifies, and the membrane became a bone. So it's not bone yet, but it's newly calcified bone matrix. Now, those osteoblasts that were inside ossification center, now they are trapped inside this calcified matrix, and they change into osteocytes. So trapped osteoblasts become osteocytes. Step number 3, woven bone and periosteum form. Accumulating osteoid is laid down between embryonic blood vessels in a random manner. That means, remember, we already get differentiation of the mesenchymal cells into osteoblast. So osteoblasts start depositing osteoid, and osteoid calcifies. Now, this osteoid is laid down between blood vessels, embryonic blood vessels, so it has kind of like a random pattern. The result is a network instead of lamellae, because lamellae are, we have the concentric lamellae that make osteon in a compact bone, but here instead of lamellae, we have trabeculae. So those parts of the bone matrix called trabeculae. And this type of bone is called woven bone. Vascularite mesenchyme condenses on the external face of the woven bone and become periosteum. Now, we still have our membrane on the surface of the bone, right? It's still our mesenchyme. Now, this part gonna condense and became a covering of the bone that is called periosteum. Step number 4, lamella bone replaces woven bone just deep to the periosteum and red marrow appears. Now, trabecula just deep to the periosteum, so we would have this, trabecula here. That's our periosteum. So those trabecula, they thicken and are later replaced with mature lamella bone. And lamella bone, this is our compact bone, forming, that says here, compact bone plates. Now, spongy bone inside, called diploid, consisting of distinct trabeculae, persist internally, and its vascular tissue becomes red marrow. All right, so if we just review what we already covered. So we started with ossification center, right? We formed this woven bone. But then osteocytes, just on the surface, they change the pattern of deposition of this matrix. So now they start producing lamellae, so they start producing compact bone. And we end up with spongy bone inside, right? Those cavities and these vascular blood vessels. So this vasculature, the blood vessels will form red bone marrow, and we will have those cavities between trabecula. So we will have compact bone on the surface and periosteum covering the bone. So we have like a flat bone is a spongy bone that is sandwiched between two plates of compact bone. And flat bones, the same as regular long bones and short bones, covered by membrane called periosteum. So that's the end of intramembranous ossification, right? So we'll go over it very quickly. So we form ossification thinner when mesenchymal cells differentiate into osteoblast. Osteoblast start depositing osteoid calcified. Osteoid is deposited in a random manner around embryonic blood vessels. Mesenchymal tissue at the surface became periosteum, and then osteocytes that on the surface of the bone start depositing osteoid in a circular manner, so it start producing compact bone instead of this woven bone. So woven bone became spongy bone. We have spongy bone between two plates of compact bone, and we have now the membrane that covers that is periosteum. Right? So that's how flat bones are formed. Now let's look at formation of long and short bones. So we're gonna look at the diagram first, and then we'll go through the steps. So let's look at the diagram. So we're gonna start with the hyaline cartilage model. So first, bones are made of cartilage. So, and again, we start with mesenchymal cells, the same as we did in intramembranous ossification. Remember, those mesenchymal cells are our embryonic cells that form a membrane. But in intramembranous ossification, mesenchymal cells differentiate directly into bone cells, osteoblast. Here, mesenchymal cells first differentiate into chondrocytes, so into cartilage, and we form precursor, a model of a bone that's made of cartilage, right? Then we need to replace this cartilage with bone. That's gonna be our goal, and that's gonna be our endochondral ossification. So first, the bone color forms around hyaline cartilage model. So we form here bone color. Then cartilage inside the center of diaphysis calcifies and dies, right? The cartilage calcifies and dies and develops the cavities, right? So you can see area of deteriorating cartilage matrix and cavity is forming. Then we have periosteal bud, and periosteal bud is made of blood vessels, and it brings bone cells into the cavity. Now we have this empty cavity, so we're gonna bring osteoblast, right? And this osteoblast start forming spongy bone inside this cavity. But this periosteal bud also brings osteoclast, and osteoclast start removing those debris of the cartilage, right? Because we had a cartilage at the beginning. So if cartilage dies, we need to clean up this area. So that's why we have our white blood cells, macrophages, osteoclast, and we start cleaning up this cavity. We actually even destroy some of this spongy bone that was formed in the middle of the diaphysis. So the diaphysis elongates and medullary cavity is formed, right? Medullary cavity is formed because we deposited spongy bone. Now osteoclast gonna resorb the spongy bone so we can have cavities. And ossification, so cavity forms as ossification continues. And so cavity will receive these blood vessels, and we will end up with at the beginning, you know, when we young, when we just born, it will be red bone marrow in this cavity to begin with. Then it will be replaced by yellow bone marrow. Now, when we're done with the middle of the diaphysis, then secondary ossification centers appears in the epiphysis. And prepare us for stage 5. So the epiphysis ossifies. When completed, hyaline cartilage remain only in epiphyseal plates and articular cartilage over here, right? So now let's go ahead and kind of read in the detail. So in more details, what's going on. Right, so that's our previous 2 slides. So endochondral ossification. Bone is developed in hyaline cartilage model. So we already know that, right? We're going to start with hyaline cartilage model, and then bone will be developed from this model. It will replace the model. It's not like your cartilage became a bone. It just cartilage will die, and bone will replace this cartilaginous model. Endochondral ossification is development of short and long bones. So in the middle of cartilaginous diaphysis, so here we have our, remember, bone, and this in the middle we have diaphysis. On the surface, a color of bone tissue gives rise by intramembranous ossification. From this time, the perichondrium is called periosteum. So remember, I will go back over here that we said that we're gonna start formation of bony color. Now, how do we call this bony color? This is called through intramembranous ossification. That makes sense? Not endochondral, but because the cartilage is covered by tissue called perichondrium, and we still have mesenchymal undifferentiated cells over there. They will differentiate into chondroblast, and they start depositing this bony color, right? That's what happened in step 3. Now, from that moment, we call perichondrium periosteum. Now, one primary ossification center occurs in the middle of future diaphysis. So primary ossification center occurs right there in the middle of diaphysis, and diaphysis is the shaft of a long bone, right? Chondrocytes enlarge. We call it hypertrophy of chondrocytes. And then they die. So the chondrocytes start depositing lots of calcium, they get larger, and then we have disintegration of the cartilage. So the cartilage is dead inside, and it's replaced by bone tissue. Between new bone trabeculas, the bone marrow cavity is formed. Ossification continues longitudinally towards both epiphyses, right? So here we continue ossification toward the end of a bone that's called epiphysis. Oops. Then two secondary ossification centers in both epiphyses occur later. Hypertrophy of chondrocytes occur later, right? Two secondary ossification centers, I'm sorry, this is a spelling mistake, in both epiphyses occur later, right there. We have the formation of secondary ossification center in both epiphyses. Now, what happened? It again, chondrocytes be enlarged. We have hypertrophy of chondrocytes. They start calcification, so they start secrete calcium. And when chondrocytes calcify themselves, they die. They cannot survive because cartilage is a vascular tissue, so it's require oxygen and nutrients by diffusion. And if you have matrix that became calcified, the chondrocytes just die. They don't receive oxygen and nutrients, and they replaced by bone as well in the epiphysis. That's how formation of spongy bone happen in the epiphysis of a long bone, right? So let's look over here. So again, we start with formation of bony color, right, through intramembranous ossification. Then the cartilage inside the diaphysis enlarge and start secreting calcium, and it dies, forming this cavity. Then this cartilage that was inside the diaphysis is replaced by bone. Then we start formation of secondary ossification center in the epiphysis, and we form spongy bone in the epiphysis. Right, in the same time, the medullary cavity form inside the diaphysis. So cartilage on future articular surfaces persists through adult life. So the cartilage stays in the articular surfaces, right over here, articular cartilage on the surface of the epiphysis. And between epiphysis and diaphysis, we have growth plate, that is hyaline cartilage, that also remains to the age 18 to 20, and it's responsible for growing bone in length. Right? Okay. So I know it might be a little bit confusing, maybe how I explain it, but I don't know. I don't want this video to be too long, but I guess I might need to repeat it one more time. So we start with formation of cartilage, right? Cartilaginous model of long bones. Now, how this cartilage is formed? It's formed from that mesenchymal cells. So mesenchymal cells differentiate into chondrocytes and form bones made of cartilage, right? Now, cartilage is covered by perichondria. It's a membrane. In the perichondrium, you still have stem cells, undifferentiated stem cells, and they differentiate into osteoblast, and they start forming this bony color. Now, when the bony color is formed, the cartilage inside the diaphysis have difficulties receiving oxygen and nutrients, right? Because there is like a very hard bony color. And of course, the bony color cover entire surface of the diaphysis, so it goes all around. Now, this cartilage inside start growing big, so it's hypertrophy of the cartilage. And those chondrocytes that are large, they different from regular chondrocytes. So they start depositing calcium, and this kills them completely, right? So now we have the area of deteriorating cartilage matrix. At the same time, because we are still inside the uterus, right? We still develop, organs, and blood vessels are growing. We have a blood vessels growing toward this area, toward this area inside the long bone. And those blood vessels we call periosteal bud, and it brings bone cells, it brings white blood cells, it brings osteoblast and osteoclast and macrophages. And macrophages start cleaning up the debris of the cartilage. Osteoblasts start depositing spongy bone over here. Then osteoclasts start cleaning up the spongy bone, forming medullary cavity that is filled with red bone marrow, right? And this ossification, so cartilage continues to die and replaced by bone, and it continues longitudinally toward the epiphysis. Then later, we have a secondary ossification center in epiphysis. It can be in both epiphyses, it can be in one epiphysis only, depends how long this bone is. And the process pretty much begins, cartilage enlarges, we have hypertrophy of the cartilage, cartilage start depositing calcium, cartilage dies and replaced by bone. And we have a spongy bone in epiphysis. We have a spongy bone and a cavity in the diaphysis. And the diaphysis on the surface, we have a compact bone. Right? And everything is covered by periosteum. Now we do have some remain of the cartilage. It's articular cartilage on the surface of epiphysis that is, remains our entire life, and the cartilage between epiphysis and diaphysis called epiphyseal plate that will, this cartilage still will divide and allow your bones to grow longer. And at the age 18 or 20, we use all of this cartilage, and instead of epiphyseal plate, we have epiphyseal line, and the growth, longitudinal growth of bones, of long bone stops, right? Okay. Thank you for staying with me through all this explanation. All right, so here are some conditions: achondroplastic dwarfism and Cleidocranial dysplasia that affect ossification. Achondroplastic dwarfism is a genetic condition, genetic disorder that affects development of long bones. And here is a Peter Dinklage, American actor who is famous, especially by his role in a Game of Thrones. Now he has this achondroplastic dwarfism when his long bones do not develop properly. And Cleidocranial dysplasia, that's genetic disorder that affects intramembranous ossification. And this is another actor, I don't know how to pronounce his name correctly, Gaten Matarazzo. He worked, he played a role in Stranger Things. So he has some abnormalities in formation of mandible, clavicle, and some cranial bones, because that type of disorder affects formation of flat bones, cleidocranial dysplasia. So that was ossification through embryonic development. We also have postnatal bone growth. So bones can grow longer and wider. So when bones grow longer, we call it interstitial growth. Interstitial means between tissue. And when bones grow wider, we call it appositional growth. It increases the thickness and remodeling of all bones by osteoblast and osteoclast on bone surfaces. And bone is grow in diameter. So we will talk about interstitial growth over here. Now, interstitial growth happens inside this epiphyseal plate. So the bone actually, for the bone to become longer, right? We have this cartilage inside epiphyseal plate that will divide and increase the length of a bone, and then the cartilage will be replaced by a bone, similar to endochondral ossification, right? So So here we are looking at epiphyseal plate at the cartilage, and cartilage is organized into 4 important functional zones. So we have first zone that is not shown over here. It's a resting zone, right? So it's a reserve zone, a reserve or resting zone. But then we have proliferation or growth, hypertrophic, calcification, and ossification. So now let's look at those zones on our next slide. So here we have our resting cartilage, and so you will see just a chondrocytes inside the lacunae and matrix. So it's similar to hyaline cartilage, and then proliferation zone. So cartilage cells undergo mitosis. Proliferation means we have more, right? So we proliferate, so we divide, or cells divide, forming new cells. And in the proliferation zone, you will see we have these stacks of chondrocytes. You see this like columns. Then hypertrophy or hypertrophic zone, all the cartilage cells enlarge. And now you can see the cells became bigger, right? So hypertrophy means cells became bigger. When we have cartilage cells that go through hypertrophy, remember they start secreting calcium. So next is our calcification zone. So matrix became calcified. And when matrix became calcified, it became hard, right? So the hard matrix surrounding living cells. So these cells that depends on diffusion to receive oxygen and nutrients and get rid of carbon dioxide and waste product. If you have hard matrix surrounding the cells that depends on diffusion, the cell will die, right? That's why cartilage cells die. And matrix begins deteriorating. And so the cartilage dies. Now, this towards the epiphysis, this is towards the diaphysis. In the diaphysis, we already have a bone. So we have bone cells, osteoblast and osteoclast, right? So, so when we have cartilage that is dead, we're going to replace this space with bone tissue. So we have here osteoblasts that start depositing bone matrix and secreting osteon. So that's our ossification zone. New bone formation is occurring in the ossification zone. And that's allow bones to grow longer. Because look, if we go back over here, so if we have cartilage that divides right there, and it's divides over here, and then it divides, and then it's replaced by bone, the bone getting longer. So you divide here, right? So you grow longer. You divide over here, and you grow longer. So the entire bone get longer. Right? So that's what we call interstitial growth. And it's happen not on the surface. It happens inside the tissue. That's what interstitial means. Right, so now let's look at the how bones grow in diameter, oppositional growth. So this is what happened over here. So the bone formation, so we're gonna start a picture over here that shows us bone formation at the surface of the bone that produces ridges that parallel blood vessels. And so here we have formation of bone now on the surface, and we produce these ridges. The ridges enlarge and create deep pockets. Then the ridges meet and fuse. So you can see the ridges meet and fuse, trapping the vessels inside the bone. Bone deposition proceeds inwards, right? So here we have too big of the canal. So deposition proceeds inwards towards the vessels beginning the creation of typical osteon. So here's our typical osteon. Additional circumferential lamellae are deposited and the bone continues to increase in the diameter. So those lamellae over here are called concentric lamellae, and then we start depositing lamellae on the surface of the bone that are called circumferential lamellae. Now, osteon is complete. So here's our osteon. It's complete with the new central canal. So here, new central canal around the blood vessels. Second blood vessels become enclosed and the process continues. Right. So here we have a bone grows in a diameter as new bone is added to the outer surface. At the same time, osteoclast resorb bone in the inside, enlarging the medullary cavity, right? So at the same time, we not only, because we don't want a bone just getting larger in the diameter and the cavity stays the same. So we remodel the bone by resorbing bone inside the cavity, enlarging the cavity, right? So osteoclast resorbs old bone, osteoblast produces new bone, and bone remodeling happens through our entire adult life, and 5 to 10% of skeleton is renewed annually. So every year, 5 to 10% of your skeleton is in new bones. All right, but when we remodeling the bone, so when the bone, let's say when bones have grow longer and wider, and I just want to remind you that the bone increases in length until we still have this epiphyseal plate. When we use all this cartilage, bones cannot get any longer, so you cannot be any taller. So your growth stops at age 18 to 20. So when you're 18 or 20 years old, you don't grow any taller, right? That's because you don't have this cartilage in the epiphyseal plate anymore. But bones still will grow in a diameter. They continue growing in diameter. But now imagine if your bone grow longer and wider, you need to remodel it because you still need the same shape of a bone, right? So that's what this diagram shows. It's not just your bone grows, you constantly remodel your bone. So bone is resorbed over here and bone is added right there, right? So resorbed inside the cavity. So that continues through our adult life. Now, how the growth of bone is regulated. So growth hormones stimulate epiphyseal plate activity. That growth hormone is released by your pituitary gland that is located in your cranial cavity. Then you have a thyroid hormone that modulate activity of growth hormone, and we have testosterone and estrogen at puberty that promote adolescence growth spurts and also end growth by inducing epiphyseal plate closure. So not only so those sex hormones, male and female, they promote your growth, and at the same time they close the epiphyseal plate, so at the end of the puberty, you do not grow any taller. We also have bone deposition that occurs where bone is injured or added strength is needed. Bone deposition require diet rich in protein, vitamins C, D, and A, calcium, phosphorus, magnesium, manganese. Calcium is necessary for formation of your bones, but calcium plays a really critical role in our functioning and keeping our homeostasis. Calcium is necessary not only for bone formation, but also for transmission of nerve impulses, for muscle contraction, blood coagulation, secretion by glands and nerve cells, and cell division. So you can see the calcium is really very critical mineral in your diet. So how this calcium level is regulated? Now, the normal calcium homeostasis in blood is about 10 milligrams per 100 milliliters. So it's 9-11 milligrams, so we can just remember 10 per 100. Now, when the level of calcium in blood drops, so falling blood calcium level, that's a stimulus. So now your body is out of homeostatic balance. This will activate parathyroid glands to secrete parathyroid hormone. Now, parathyroid glands are 4 glands on the posterior side of the thyroid. Now, what this parathyroid, so you don't have enough calcium in your blood, right? So you need to take calcium from bones and secrete it into blood, right? So the level goes up, because if you're falling, you need to go back up. So that's negative feedback. Now, this parathyroid hormone, it activates osteoclast, and they degrade the bone matrix and release calcium in the blood, and we returning back to homeostatic balance. Of course, we have also thyroid gland that secrete calcitonin. So calcitonin is decreasing calcium level in blood. So parathyroid hormone increases calcium in blood, and calcitonin secreted by thyroid hormone decreases blood calcium. So they work as in a balance. However, parathyroid is a major hormone that regulate blood calcium level. So I would say the parathyroid is more important than thyroid gland in calcium homeostasis. Response to mechanical stress. A bone grows or remodels in response to forces or demands placed upon it, and it's called Wolff's law. Now that means that if you, for example, start if you go to a gym and start weightlifting, if you put lots of force on your bones will grow thicker. Now, observations that supports Wolff's law. Hardness, right or left-handed, results in bone of one upper limb being thicker and stronger. So if you're right-handed, the chances are that bones of your right hand are thicker and stronger than bones of your left hand. Now, curved bones are thickest where they're most likely to buckle. That's where we have this force, mechanical force. Trabecular of spongy bone form along lines of stress, and large bony projections occur where heavy active muscles attached to the bone. So those are all observations that supports Wolff's law. And the Wolff's law explain, why we deposit more bony matrix in the area where we have more stress. So let's look over here. So here's your long bone, and you have, so that's a femur, right? So here's your body weight over here. So you put a force on the head of the femur, and you have this compressive force on your bone. At the same time, because the bone is curved, you have tension force here. Now, when we have unbalanced compressive here and tension here, then you will deposit more bones in this curved surface of the bone, right? So where you have more stress, you will have a deposition of the bone. Wolff's law also explains why we can have bones that are hollow inside, why we can have the medullary cavities and bones still stay strong. Because in the middle of the diaphysis, you actually have a point with no stress. So if you have compressive force and you have tension force that balance each other in the middle of the bone, and that allow you to have a cavity inside. And at the same time, you don't break your bones because they hollow inside. Classification of bone fracture. Bone fracture may be classified by 4 either-or classification. Number 1, position of bone ends after fracture. Non-displaced ends remain normal position, and displaced ends out of normal alignment. Completeness of the break. Complete, broken all the way through the bone, and incomplete, not broken all the way through. Orientation of the break to the long axis of the bone. So long axis is this one. Is it linear, parallel to long axis, or transverse, perpendicular to long axis? So if this is your bone, so linear will be parallel and transverse going to be perpendicular. Whether or not the bone ends penetrate the skin, compound or open, the bone ends penetrate the skin, or simple or closed, bone ends do not penetrate the skin. And so here's some other classification that we can add. So we have transverse over here, occurs straight across the long axis of the bone. Oblique occurs at the angle that is not 90 degrees to the long axis, because if it's 90 degree, then it's transverse, right? If it's not 90 degree, then it's oblique. Spiral. Bone segments are pulled apart as a result of twisting motion. Comminuted, several breaks result in many small pieces between two large segments. Impacted, one fragment is driven into the other, usually as a result of compression. Green stick, a parallel fracture, partial fracture in which only one side of a bone is broken, common in kids. Open or compound fracture at which at least one end of the broken bone tears through the skin, carries a high risk of infection. Or closed or simple fracture in which the skin remains intact. And I have slides that show you example of different bone fracture. So here's our transverse, here's the linear, here's oblique, here's oblique and displaced. And it can be open or closed. We don't know if it breaks through the skin, it's going to be open. If it does not break through the skin, it will be closed. Here's a spiral, green stick, when the bone is not broken all the way through, and comminuted, when you have several pieces between two broken parts of the bone. And the last topic of this lecture is stages in the healing of bone fracture. So we're going to start with hematoma. Torn blood vessels, hemorrhage. So your bone is very vascular organ, so you have lots of blood vessels. If you break through the blood vessels, you have bleeding and formation of hematoma. Hematoma is a clot. So clot, hematoma forms, side became swollen, painful, and inflamed. And then you start your healing process. We're going to start this with formation. Oh, actually, inflammation is the beginning of healing process as well. So the second stage is fibrocartilaginous callus is formed. Phagocytic cells clear debris. So you will have debris of blood vessels, broken collagen fibers, cells, matrix of a bone. So we need to clean the debris. Osteoblast begins forming spongy bone within 1 week. Fibroblasts secrete collagen fibers to connect bone ends, and mass of repair tissue now called fibrocartilaginous callus. So we have this callus over here, and we have external and internal callus that is made of fibrous tissue and cartilage, and some of the spongy bone. Then bony callus is formed. New trabecula form a bony callus, and bony callus formation continues until firm union is formed in 2 months. So we replace fibrocartilaginous callus with bony callus. And then we have bone remodeling. Is in response to mechanical stressors over several months, and final structure resemble original. So here we have these 4 processes: hematoma is formed, fibrocartilaginous callus is formed, then bony callus is formed, and then we have bone remodeling, right? And those are stages in bone healing of a bone fracture. The only thing I think over here it might be a little bit confusing, because it says even when we form fibrocartilaginous callus, we start the formation of spongy bone within 1 week, right? So it doesn't mean that kind of you form the cartilage completely, right? You form this cartilaginous callus, but remember what happened with your cartilage. Cartilage became enlarged, so we have hypertrophy of the cartilage. So cartilage start getting larger, start secreting calcium. So processes are very similar. And then cartilage start dying, and it's need to be replaced by bone. So that's what we have replacement from a week 1. Within 2 months, we start replacing this cartilage by bone. Okay. Thank you guys for watching, and I hope it was helpful. Let me know if you have any questions, or leave a comment in a comment section, and I will get back to answer your questions. And again, have a nice day. Thank you for watching. I hope it was helpful.